talk I've originally created for kernel recipes conference last year, which is like a more kernel newbies level audience. So I guess some of the things I will explain will be familiar to you, but I hope there will be also some things that you didn't know, because even myself, when I prepare these talks, I always like learn a lot myself about some of the obscure things that I've never checked before, and learn about their history, and then become sad why is it like that and why it cannot be changed anymore. We'll see some examples of that today as well, and the topic also fits to the topic of observability that we discussed in the morning, and we'll also see examples about how the observability would be nice, it would be better, but it would be too performance prohibitive. So we're discussing about where the memory is used in Linux on the kernel level, process level. So we'll start with the very basic overview command that everybody knows. That command is free, and these days it will show you these kinds of values. I think they were expanded some time ago. Some of the columns were not there before. And yeah, we might try to think about what's behind those values, even if we didn't check the source code, and try to just do some simple math, whether it all makes sense. And suddenly we find out that if we, for example, try to add used to free, we get the value of like 1900, but the total memory is 32 gigabytes almost. So even that simple comparison doesn't seem to make sense. So yeah, so used plus free isn't total. So what's going on? So we've run right straight into the main principle of Linux memory management, which means unused memory is wasted memory, and that means that like some memory will be allocated by our processes, and it's used by them, and so that's a given that it's used. But also any free memory, the kernel will try to put data in it in case the data can be accessed later, and it will save I/O costs. So the main consumer of that is the so-called page cache, which every file that's touched by some process and will bring the data to memory or be written to the file will also try to stay in the page cache to make further accesses faster, and this means that the memory that will be really free, that will only be in the system for a short time after boot, and as the longer the system runs, the more memory will be in the page cache, and suddenly the free doesn't make much sense because it's always close to zero. And so we have to have some better like metric to think about how much is free for the user space if it wants to request more memory. So we can see there's a column that's called buffer and cache, and that seems like it might be the page cache thing I just explained. So maybe used and free plus the cache will be equal to the total, and yeah, that looks a bit better, but it's more than the total, so maybe some of the cache is actually considered used to make it really equal. Or we can try to see if the free and cache is the same as the available column, and it's again closed close, but still not perfect. Then we can finally realize that used and available is almost equal to total modulo some rounding error, and this looks promising, and this is actually how the free command works, but we don't know yet what exactly is available, and I haven't explained what's the shared column. And so the next step is to look at, because the free is just a user space command, it has to get the data from somewhere, from the kernel, which has all the accounting inside. And for the least comprehensive view, the free output, we can go to the most comprehensive view, which is the pseudo file called /proc/meminfo, which has all the counters that describe how memory is used in the Linux. But yeah, actually there are so many that the letters are tiny, so I can remove the title, but there's still too many. So let's just quickly drop some of them that are not so relevant. So we have these counters that actually don't describe occupied memory, but some in-kernel data structures or page tables that are used to access the physical memory. So these are not memory usage counters, so let's just ignore them. There are some counters related to huge TLBFS pages. They are not even comprehensive enough because they describe only one possible size of the huge pages, but there can be multiple size, and the details for there are elsewhere than in this file, so let's ignore them. Then we have counters of how much memory was reported to have ECC errors, so the kernel doesn't use it anymore, which might be interesting if it's not 0, but otherwise it's not that interesting. CMA is something that is used mostly by Android phone hardware. Unaccepted is a new counter that may be non-zero shortly after boot on confidential computing guest, and then later the memory will be eventually accepted and it will go to the 0. So with those counters removed as not so interesting, we now have space to put also the free output there and see that really some of the values that are in the free command correspond exactly, or you have to trust me because this is rounded up differently. They correspond exactly to some of the counters in the proc meminfo, and used is calculated from the total minus available, as I said, and doesn't have a direct equivalent in the proc meminfo. The next view we can take on these remaining counters is try to divide them into counters that measure memory that's directly used by user space, that's the green ones, and memory that's used by the kernel itself, although it might be also on behalf of user space. And the gray ones are, again, some counters that don't describe used memory. And the italic ones are like redundant, so they describe the same thing as different counters, but in a different kind of direction. So you cannot just add everything up and expect to be equal to the total because some of them are redundant. So if we go through the gray fields, we have the memory total, which sounds obvious what it is, but there are some details to it as well. It doesn't match the actual hardware amount of RAM in the machine because some of the memory will be allocated early in the boot, and this describes only the memory that's used by the main page allocator of the kernel, so it will be always less than the physical amount of RAM. And it can also change over time with memory hot plug remove, and even in the guest ballooning drivers, when the host hypervisor wants the guest to free some memory through the ballooning, this will actually be reflected in this counter, but only for the ballooning drivers that are in the kernel itself, which I think is KVM, but on some Azure or VMware, I think they don't change these values. So if you see some surprise drop of the total memory, it might be due to that. Then we have, for example, memory occupied by ZSwap, if you have that enabled. And yeah, this is how much the compressed data occupies of the physical RAM, and the complementary counter that's not saying how much memory is consumed, so it's gray. It says how much was the size of the original pages before they were compressed, and this can be used to see how effective the compression is, for example. Then going to the rest of the kernel counters, we have one counter for all the memory occupied by the slab allocator. If you want to see the breakdown of which kind of objects, how many of them there are, and like the entries, inodes, then there's another proc slab info file with all the details. But also large allocations using the kmalloc interface will be counted toward the slab counter, but not be visible in the proc slab info. So if you see some inconsistency, it might be these large kmalloc allocations. Then we also distinguish slab caches that can free their objects on demand. That's called reclaimable. And so this means this memory can be somehow also available when it's needed, but it's not as easy because if you free some objects from the slab pages, it doesn't always mean you manage to free the whole pages, because some of the objects might be in reclaimable caches but not be reclaimable at some given moment. So it's not as easy as reclaiming the page cache. Then I noticed that there's this k-reclaimable counter that has the same value as reclaimable. So I said, what's going on? Why is it here? And check the git blame history, like who added this useless counter. And of course it was me, as you can guess. But it was many years ago, and I already forgot. And the reason was that at the time there was this ion allocator for GPU drivers, which consumed which could consume substantial amount of memory, and it wouldn't be visible in the meminfo, so it seemed like a good idea to edit there. But since then, they replaced this allocator with something based on shared memory, so it's no longer useful. I mean, if we find some consumer that would fit, we can edit. But right now, it's just the same thing as the slab, and we cannot really, or we never dare to remove any counters that are added, because some programs might be parsing the file and expect them to be there, and suddenly if you remove it, you are breaking user space, and that's that's always a bad idea. So we're stuck with that, and it was a lesson that when adding things to the kernel API or ABI, one always has to be careful, because then you're stuck with them forever. Yeah, another kernel consumer of memory are the stacks of processes that are used when the processes enter the kernel. So every kernel, every user space process will also have its kernel stack in case it wants to do a syscall or is interrupted by an interrupt. And also many user space processes need page tables to function. So we know how much memory is occupied by those. And if we have some secondary page tables for things like KVM guest or IOMMU, they also have their own counter. Yeah, and like the K-reclaimable, there are also some historical counters that cannot be removed and now are 0. So there was this NFS unstable counter. Bounced buffers are something that were still not removed, but I think once that happens, there will be another counter that will be always 0. But yeah, I think modern file systems don't need them, so it's mostly 0 anyway. Fused file systems also need some temporary buffers, especially handle it when they need to write data back, because they have to submit them to user space processes, which is more tricky than doing it from the kernel. Just this LSFMM, there was discussion about how this could be improved, so maybe this will also become a historical counter in the future. Then there are these cryptical values that talk about commit limit and committed AS. So the committed AS is like the sum of all address spaces of all user processes. Not all of the address spaces, but most of them, those that can contain private writable memory, which is anonymous or even files. And so that's basically tries to estimate how much the kernel promised to the users, to the user processes, that they can consume memory, but the promise is always much higher than the total amount of the memory, because Linux does normally something that's called overcommit, because it actually never expects those processes to fill all the memory with private pages. So it would be otherwise wasted. So we accept some risk and then hope for the best. And if at the worst case, there's OM killer to save us. So, for example, in this case, you could see that on the desktop where I took this snapshot, the committed amount was already over the commit limit. But because the VM overcommit memory mode is different than this value of 2, which means never things continue working. But might be interesting experiment to try going over this limit and then change it to overcommit never and see what happens. But I wasn't brave enough to try that. It would be a bad idea during the presentation anyway. Yeah. Probably the most useless counter I found is this one, which says what's the virtual memory area that kernel has reserved for VM allocations, but it's just a reservation in the virtual address space. It doesn't mean any of that is actually used. So it comes down to this absurd number that it's so large that it breaks the formatting and justification. The much more useful is the second counter, which says how much of this VMLOC is actually populated and is consuming any memory. Then there's another historical thing that's 0 again, because the VMLOC implementation changed meanwhile and doesn't use those chunks anymore. Yeah, and the last kernel counter is for per CPU data, which is something that is used in the kernel, but if it was suspiciously high, it might mean this kind of allocations are leaking. Yeah, so that was the kernel counters and the non-counters. So now let's look finally at the user space memory, which was the green one. And for that, we also have to realize that there are two kinds of user space memory. I already touched on it a bit. The page cache is populated by files, and the anonymous pages are populated by the processes doing mmap with map private and map anonymous, and then writing some data into them. And this data is not connected to any backing storage. So if it has to be reclaimed, it can only be swept out to the swap partitions or files. And this makes it very different from the page cache. So that's why we distinguish that almost everywhere. And page caches are the user space data that are backed by files and can be, unless it's overwritten in the user space, it can be simply discarded when needed and read it back from the files when needed. If it's written to, it has to be written back to the files and then can be discarded. And I said there are two of them, but there's always a by one error. So there's a third one called shared memory, which behaves a bit like both of them. So it's considered to be part of the page cache because it can outlive the processes that created them. For example, files in the TMPFS, but it has no persistent storage, so it can be only swapped out like anonymous pages. So there were many counters, the green ones, that talk about these three kinds of memory I just described. And to make an instance of them, I've created these Venn diagrams. So first, the anonymous counter. So we have counter of anonymous pages. That are those created by mmap with anonymous and private. Some of them will be transparent huge pages, so there's another counter for that. And there's this clear subset relation. For the page cache, it's much more complicated. We have this cached counter in proc meminfo. That's the whole page cache, except the buffers have a separate one. But the free comment, I think, sums them both together. shmem, the shared memory, will be part of the cached counter. Then some of these page cache pages can also be huge these days, transparent huge pages. So they have another counter, but that can include both shmem and real files. And there's a special counter for those huge pages that are shmem. So if you need to, you can get the amount for each of the possible combinations. Then we have also counters, for some reason, for how much of this page cache is mapped by any processes. We don't have that special counter for anonymous memory because that's all mapped just by design, otherwise it wouldn't exist. But for files, we can track how much is now mapped in some processes and how much is just sitting around, which doesn't actually mean it's not used, because when there will be reads or writes, this call to the page cache sitting that's not mapped, it still makes sense to have those in the page cache to not need to access the storage. Yeah, so again, for this, I've put the cached and buffers together, otherwise it will be just too much, the diagram, and part of it, again, is SHMEM. Then part of the broader thing can be mapped by processes. Subset of the shared memory that's mapped doesn't have any special counter. Then some of it might be so-called PMD mapped, which means it's mapped as a transparent huge page. And that also doesn't have a counter, but we have counters for how much is mapped by huge page, that's files, and how much is mapped by SHMEM. So yeah, it's all very consistent and gives you a clear picture if you need it for some reason. Then another view on this user space memory is can be provided by the counters that count how much of it is active and inactive, which is a bit of implementation detail of how the memory reclaim works. It tries to divide more hot or recently accessed pages from the least lesser recently accessed pages, and processes them at a different rate to work as optimally as possible. And so we can observe how much is now in those active and inactive lists. And this is given separately for the anonymous and page cache memory, because they behave very differently from the reclaim perspective. And there's a bit of a twist. So the SHM, the shared memory, is part of the page cache, so it's part of the cached counter. But because it behaves like anonymous memory and has to be swapped out, it's counted against the anonymous active and inactive counters. There might be also some unevictable or unlocked memory that is not considered active or inactive, but there's usually not so many of that. So we can do this cross-check, like try to sum together anonymous memory and shared memory and see if the result is the same as the summing of active and inactive anonymous LRU counters. And we can see that it's almost matches. There will always be some pages in some intermediate per CPU caches that will mean it will not be exactly the same, but it's almost the same. And for the file side, we can do the same, but we have to subtract the SHMEM in this case, because it's not on the file LRU, but on the anonymous LRU. And yeah, I've seen actually cases where these things don't match, and the LRU values were much larger, and it usually means there's some kind of memory leak. Some memory should be freed, but somebody has increased the ref counter on those pages, so they stay in the LRU lists, and this can be used as a cross-check whether this kind of leak is happening. So that's it for the proc meminfo. And yeah, as a final change, I've also made in bold font those values that you can sum and expect the value to be equal to the total or close to it. So in example of this listing, yeah, when I sum those bold counters, I get almost those 32 gigabytes. And the difference is only 572 megabytes, which is not accounted in any counter, which is actually a good result, because there are many allocations in the kernel that just grab some pages and don't have any counter in the proc meminfo. And as you could see, adding everything there would make it even longer and risk getting some more historical baggage that cannot be removed anymore. So I've seen in various bugs examples where, for example, XFS allocations were doing lots of these allocations and were not accounting. Or I think networking stack also has something for the buffers, but it has some counter actually for TCP or UDP, but it's somewhere else. But this can be used as a basic check whether something is leaking or not. But there's no exact value that says it's good or bad. But if the difference grows over time of the system lifetime, that means something might, for example, be leaking memory. And I'll get a bit later to what can be done about that. But finally, I should also explain what's the MemAvailable. That now very important counter for the free command. And we see it was very close to the free and cache amount, and actually that's really the case, because it counts the number of pages on the file lists or the LRU list, and also the reclaimable slab. It assumes that not all of that can be actually reclaimed, so there's always some reserved part that's subtracted. And if we didn't subtract them, we would get this value, but the MemAvailable is actually a bit lower. So it actually an estimate of how much memory can be reclaimed or is already free if user space processes needed it. Then that was the kernel wide view, but we might also want to know how much our processes, individual processes, are using memory. And for that, the tools like PS or top or HTOP always have these two counters. One is called VIRT or V size, and that says how large are the virtual area sizes of the processes, which is not something that's immediately occupied. And there's a res or RSS that counts how many pages are actually populated by mapping anonymous or file memory. And as we'll see, it's also not perfect. So it can be quite misleading. Consider this program that when I put the slides online, there will be a link to it. But what it does, it creates a memory area and then forks the process, which should mean there are now 10 children processes with the same gigabyte memory area, and then each of the childs writes into the same memory area. And we can observe what it does in the PS output or in the free output. So after we create one process with this gigabyte area, we have we have this amount of used memory that's the baseline. We have the virtual size will be roughly the gigabyte, but the actually occupied size will be almost nothing because the area was created but not populated. And once the process writes in this gigabyte area, it populates that. So RSS is now also 1 gigabyte, and the total of the used memory increased by a gigabyte. And that's the same output again. And now if we fork the 10 children, we now see we have 10 processes which has all the RSS of 1 gigabyte, but the amount of used memory didn't actually increase by 1 gigabyte or 10 gigabytes. And only once we write in each of the child to this area, then finally the used amount of memory increased by this 10 gigabyte. But the RSS is the same, so it didn't actually tell us much about the memory usage of these processes. So what was happening behind the scenes here is that the kernel has the processes, the counters for each process that counts these RSS, the pages that are populated in the page tables. But and it's exported somewhere that the tools like PS can read that and show it to you. And if we mmap and don't use the map populate flag, it doesn't actually populate the memory. So there are no pages in the page tables that would increase the RSS. Once we write there, it happens. When we do the forks, we are creating like identical copies of the process, but they should now have independent contents of the memory. So what it does is it copies all the page tables, so they are independent, but to save time and memory, it doesn't actually immediately duplicate all the pages containing the data. It will transparently share them among the 10 or 11 processes, and only once every child writes a new data, then this, through something called copy on write mechanism, the pages become unshared, and that's only at the time where the memory usage increases, because every child gets a new copy of each page. And this is not reflected in the RSS because that doesn't know whether these pages are shared or not. It would be possible to have more accurate counter, like there's this definition called PSS, proportional set size, which could like weight contribution of each page to the memory occupation by how many processes share that page, and that would be better, but it would be expensive to maintain, because now we would have to update the counters for other processes while modifying one of them, and this would be too impractical. And yeah, even the OOM killer itself doesn't have any better metric. So in this case, if we killed one of the 10 processes, we wouldn't even gain any memory, because the memory will be still shared by the 9 other processes. So there's the way how to get this better value by getting a snapshot that's calculated on the fly by accessing this proc pit smaps or smaps rollup file, which really does the job the hard way, like walks all the page tables and counts how many pages, how many processes share each page, and and calculates this value, but it's costly, so you have to pay that cost on demand. So in this case, we could have seen that PSS would be small after the forks, and there's even also a counter of how many pages are really uniquely used by that process. And to have this more user-friendly, there's a MemTool that can show you this output similarly to the PS, and we can see that the PSS counter now works because after the fork we have values that would sum up to the 1 gigabyte and not the RSS value that looks like every one of them has already a private gigabyte of memory. Yeah. So back to how to debug missing kernel memory. When I said the counters should sum up to close to MemTotal, and sometimes they don't, and there's a memory leak. So there's a way to find out who allocated every page in the kernel, but it's not enabled by default because it does memory and CPU overhead. But the kernels we ship have this support configured in. It's called page owner, and it only takes the boot parameter page owner on, which means this will become active. It will have that overhead, but if you are debugging, you are hopefully prepared to pay it. And then we have these debugfs files that can tell us how much memory is occupied by every different allocation stack of functions that did the allocation. So here's an example of how something was allocating slab memory and with 1800 pages. Something similar exists for the slab caches, which there's just a bit different debug option that will enable this, and then you can see the similar thing for individual kinds of slab objects. There's also some new functionality in recent kernels that tries to be like more lightweight and always enabled. That's memalloc profiling, but the downside is that it doesn't have all the stacks, the complete stacks, but only the immediate caller that's doing the allocation. So when there are some helper functions that allocate from many different paths, you cannot distinguish them. So I would rather recommend using the page owner if you really need to debug memory leaks. Yeah, yes. Yeah, and tracing is also possible, but yeah, that's the last slide. So thank you for your attention.
Yeah, I didn't have a question. I just want to say that thank you for this excellent tour into most useless counters that kernel presents to poor users. And um, I think it proves an important point that you shouldn't usually care how much free memory you have or what is consuming that memory, because you do not have a full picture, and you shouldn't care. So maybe there will be another talk that will be talking about how you can actually measure whether you are using your memory properly by Michal Kotny. But please stop looking at free for the output of free command or other commands, because it will very likely give you very misleading answer and make you worried about stuff that you shouldn't be worried.
Yeah, actually, sometimes we get in. So Hannes, can you set up your laptop already?
I was wondering about the copy on write mechanism. How does that work? Does it involve the TLB, some page faults? don't
Yeah, it involves setting the pages as write protected and then capturing the page fault and realizing that it's copy on write and doing it in the page fault handle.
But I'm wondering, so the page fault is triggered even for the parent process then?
Yes.
Oh, okay. Thank you.